Hello everyone, I am Karan Mashru. Welcome to this video. In this video, we are going to discuss solution of the problem of the day, that is check for balanced tree. First of all, let us start by understanding the question. What does question say? Given a binary tree, find if it is height balanced or not. Okay, so we are given a binary tree. What does binary tree means? That a node will have either 0 children or 1 children or at max 2 children. A tree is height balanced if the difference between the heights of left and right subtree is not more than 1 for all the nodes of the tree. So for each and every node, if we check the height of the left subtree and height of the right subtree and take the difference, then that difference should not be more than 1. So either it should be 0 or it should be 1. Okay. If we look at the example here, so this is the height balanced tree, right? So here there are no left and right subtree, so the difference between the left and right subtree is how much? 0 for this node. Similarly for this, for 10 the height of the left subtree is 1, for the height of the right subtree is 0. Okay, there is one node present on the left, so here the difference is 1, that is all allowed. For 1 the height of the right subtree is 1 and height of the left subtree is how much? 2. So 2 minus 1 is 1, that is also allowed. Okay, so if we look at this example, this is unbalanced because here on the left subtree the height on the left hand side is 2 and height on the right hand side of 1 is 0, right? So that is unbalanced. Here if we here is this balanced? No. Why? Because the height of the left subtree of 1 is 2 and height of the right subtree is 0, so that is 2 minus 0 is 0, so it is not balanced, so we return 0. The maximum difference in height of left subtree and right subtree is 2, which is greater than 1, hence unbalanced. This is the balance. You can look at the explanation. You do not need to take input, just complete the function is balanced that takes root node as parameter and returns true if the tree is balanced as false. The number of nodes are up to 10 to the power 5 and the data of the node can go up to 10 to the power 9. The expected time complexity is big of n and expected auxiliary space is big of h, where h is the height of the tree. So now we need to tell whether a given binary tree is balanced or not. Okay, so what is the definition of balance? That the height of the left subtree minus the height of the right subtree should be not more than 1 for all the nodes. So if we look at the nodes here, see there is no left and right subtree here, so the difference between the left subtree height and the right subtree height is how much? 0. Here there is no left subtree and right subtree, so the difference between the left and right subtree is how much? 0. Here also it would be 0. For this, the height of the left subtree is 1 and height of the right subtree is 0. So the difference is 1. That is also allowed. Here also there are no left subtree and right subtree. So the difference is 0. For this node, left subtree height is 1, right subtree height is 1. Difference is 0. For this node, the height of the right subtree is 2. The height of the left subtree is 1. So the difference is 1. Okay, the absolute difference. For this node, the height of the left subtree is 2. The height of the right subtree is 1. So 2 minus 1 is 1. That is allowed. For this node, the height of the right subtree is basically the length of the maximum path starting from that node up to the leaf node. Okay, so we will not consider this path, we will consider this. So height of the right subtree is how much? 3, and the height of the left subtree is how much? 1, 2, 3 and 4. So 4 minus 3 is 1. That is also allowed. For this node, there is no left and right subtree, so the difference is 0. For this node, the height of the left subtree is 1 and the height of the right subtree is 1, 2 and 3. So 1 minus 3, the absolute difference is 2. So this node is not balanced, and because of that the whole tree is not balanced. Okay, this condition should hold true for each and every node of the tree. Now how will we check it? We are basically given the pointer to the root node, so what we can do is we can recursively travel up to the leaf node, and whenever we reach the leaf node, how will we know? If the left subtree and right subtree both are null, then that is a leaf node. Then we will assign a height 0 to it. Okay, and we will mark it as true. Then when we traverse up, so for example, we assigned height 0 to this, we assigned height 0 to this. Okay, we recursively traverse from here to here, here to here, here to here, here to here. Okay, and from here to here. So the height is 0 and 0. So the height of this node would be the max of left subtree and right subtree height plus 1. So the height, okay, I am talking about the height. These are the differences of left subtree and right subtree. The height of this node would be 0, this node would be 0 and this would be 1. Similarly, the height of this node would be 0. The height of this node would be how much? The height of the left subtree, the maximum out of the left subtree height and right subtree height plus 1. There is no right subtree height, right? So the height would be 0 plus 1, 1. the height of this subtree would also be 0 because it is a leaf node. Now for this, the height of this node would be how much? The height of the left subtree and out of the height of the right subtree. I'll take the max out of them and add 1. So this is 0, this is 1, okay, because here there are two nodes, plus 1. So max of 1 and 0 is how much? 1, and plus 1 will be 2. So the height of this subtree is how much? 2. So in this way, first of all, we will calculate the height of all the nodes, okay. Now how will we store height? If you have seen the question, in the question our node is made up of three members. One is the data, one is the left pointer, and one is the right pointer. Now understand one thing, we need to check the height of the tree, whether the tree is height balanced or not, okay. So that what the data the node is having, that is of no use to us. Here whether it is 500, here whether it is 5 lakh, that is no use to us. So what we will do, we will in this data member of the node, we will store height, okay, because that data is garbage value for us, okay. So we will store height in that, okay. So first of all, starting from the root node, we'll recursively go up to the leaf node and assign height to each of the data members. And for each node, I calculate three things. What? Suppose this is the node, this is the left subtree, this is the right subtree. So I'll take L and check whether the left subtree is balanced or not, okay. Root left, okay. So what I'll check for this node, I'll check whether this left subtree is balanced or not, okay. So I'll check whether this node is balanced or not. So for this, whether the the height difference between the left subtree and right subtree is not more than 1. I'll check R equals to is balanced for the right subtree, okay, for the right subtree. So whether this subtree which is below this is balanced or not. So for this, and now I'll recursively get the heights. So I will have the height of this node, like it would be the max of left subtree and right subtree height plus 1, okay. I'll also have the height of the left subtree and right subtree, right. So what I will do is, I'll take C, and in this I'll store whether this node, the subtree starting with this node, is balanced or not, whether this node is balanced or not. How will I get it? If the height of the left subtree minus the height of the right subtree is greater than 1, okay. So if root left data minus root right data, okay, and its absolute value is greater than 1, okay. So in L, I'll get true or false based upon the left subtree is balanced or not. In R, I'll get true or false based upon right subtree is balanced or not. And in C, I'll store true or false based upon whether the subtree starting with this node is balanced or not. I'll do this for all the nodes when I'll call the recursion, okay. And what I will return, I'll return L and R and C. Why? Because if I want the tree to be balanced, each and every node should be balanced, okay. So for this subtree, the left subtree should be balanced and the right subtree should be balanced, and the subtree starting with this node should also be balanced. And if this returns true for all the nodes, we will get true, otherwise we will get false. So for example, here this will return true, this will return true, this will return true, this will return true, but this will return false, okay. This all will return true, but this will return false. So left subtree will return true, right subtree will return true, but this will return false. So if I take a AND between all of them, it will return false. And finally, this will also return false to the main function, telling that this tree is not balanced because there was at least one node which was not balanced, okay. Now let's look at its actual code. So now if we look at the actual code, so I have taken three variables for a particular node root. I'll call the recursively this function only. So L, R and C. If this node is null, okay, so if the root itself is null, we will return true because empty tree is balanced, okay. If root left is null and root right is null, which means this is a leaf node, I'll assign root data equals to 0. So the height of that subtree, the leaf node, is 0 and I'll return true, because if we look at the subtree of the leaf node, it is balanced because it is a single node, okay. Then if root left is null. Okay, so if the left part is null but the right part is not null, then in that case L is true, because the left subtree is null. So the left subtree is balanced, empty subtree is balanced, so L is equals to true. I'll call R to check whether it is balanced or not. Okay, and this function will return me whether the right subtree is balanced or not. And what would be the height of the current node? It would be the max of the height of the left subtree and right subtree plus 1. But since the left subtree is null, so the root data in which I am storing the height will be root right data plus 1. And if root data is greater than 1, basically root data has what? It has the height of the subtree from there, but there is no left subtree, right? So there is no left subtree. Okay, this is what? Null. Now if we look at this, suppose the height of this will be 0, this will be 0, this will be 1, this will be how much? 1 plus 1, 2. So if the root data is greater than 1, it means that on the right hand side I have a subtree starting from this node whose height is greater than 1, and there is no subtree on the left hand side. So in that case the current node is not balanced, and I will mark C as false. If that is not greater than 1, it is equal to 1. Okay, so in that case I'll mark C as true, and I'll return L and R and C. That is basically left subtree is balanced or not, right subtree is balanced or not, and the subtree represented with the starting with the current node is balanced or not. Similarly, your left was null. If right is null, then we will assign right as true. L will be is balanced for root left. And the height of the current height of the subtree starting with the current node would be root data equals to root left data plus 1, right? And similarly, if that value is greater than 1, then we will mark the current node as false. Okay, so starting with this node, the left subtree has height greater than 1 and the right subtree is empty. Okay, in this case, so we will mark C as false, otherwise we will mark C as true, and we will return L and R and C. Now let's look at this case. So the last case is that the left is also not null and right is also not null. So L will be equal to is balanced root left, R will be equal to is balanced root right. So I'll recursively call the is balanced function on left and right subtrees and store whether they are balanced or not in L and R. Okay, what would be the height of the subtree starting with the current node? So root data will be equal to root left data comma root right data, and the max of that, right, the max height of left subtree and right subtree plus 1. Okay, so plus 1 will be stored. So in root data I'll get the height of the subtree starting with the current node. If the root left data minus root right data is greater than 1, the difference between the subtrees on the left part and right part, the difference between the height of the subtrees on the left part and right part, the absolute difference is greater than 1. It means that the subtree starting from the current node is not balanced. So we will mark C, that is the current node is false, else we will mark C as true if this is equal to 0 or if it is equal to 1. And finally I'll return L and R and C. Okay, so basically whenever the left or right node is not null, we will recursively call this. Okay, then the leaf node will return true and update the height in during backtracking. All the nodes height will be updated, and every time we will check whether the current node left subtree and right subtree is balanced or not. Even at any node, if we get false, the ultimate answer would be false, because if a node is not balanced, the whole tree is not balanced. And why we will get false even if there is one false? Because at every time we are taking the AND function, L and R and C. So even if one thing is false, everything will be false. What would be the time complexity? Time complexity would be big O of n, because we are traversing through all the n nodes of the binary tree. What would be the auxiliary space? The auxiliary space would be equal to C. As such, we are not taking any extra array or space to store anything. But when we will call recursion, the recursion stack will be filled up, and the height of that stack would be how much? It would be equal to the height of the binary tree. Okay, so that stack will occupy this much space. So the auxiliary space would be height of binary tree due to the recursion stack required, and this is the time complexity. Now let's submit this code. Let's submit it. So we have solved this question successfully. I hope you understood this solution completely. Thank you.